morning.
All right, so we're now recording, everyone. And people may continue to trickle in, but I think we can make a start. So it's my pleasure to introduce Dr. Luke Kelley to deliver today's seminar. And also happy to welcome along some members of the Nanograv collaboration. The last day of our fall meeting is today, and Luke is participating in that as well. So Luke is a colleague, a friend, and someone I always learn a ton from. He's an expert in the astrophysical modeling of massive black hole binary populations from Cosmos simulations and the associated gravitational wave detection prospects. Luke got his PhD from Harvard Center for Astrophysics, working with Professor Lars Hernquist. He then moved on to his current position as a CIERA and Lindheimer postdoctoral fellow at Northwestern Center for Interdisciplinary Exploration and Research in Astrophysics. Today, he will tell us about some exciting opportunities to understand massive black holes in a variety of different ways. So Luke, it's a pleasure to have you deliver this seminar. Please go ahead when you're ready.
Awesome. Thanks so much, Steve. It's really a pleasure to be here at Vanderbilt, even remotely, and I just hope I'll be able to visit in person sometime in not too long and get to talk more with people. I was thinking about how people often ask, oh, where's the Center for Research of Massive Black Hole Binaries? And I always kind of say, oh, it's a person here or there, kind of diffuse. But really, as of the last year or two, it's kind of become Vanderbilt, like one of the kind of core locations for leading research, both on the gravitational wave and the electromagnetic side. So it's really a special pleasure to be talking here, and hopefully I'll still have something new to present that people haven't already seen. So to start out with, this figure my Nanograv colleagues have seen a million times already, but it was kind of my attempt to throw a ball of spaghetti every single aspect of massive black hole binaries onto a single plot. So I'm gonna milk it. So my plan for the talk is to kind of go through these different elements, starting with kind of formation and evolution of massive black hole binaries, starting from galaxy mergers, going all the way till coalescence. Then looking at the most pressing aspects of this, the gravitational wave signals that Nanograv is looking for in particular, also the electromagnetic counterparts, and then especially trying to emphasize the multi-messenger component of this, how you can use the electromagnetic and the gravitational wave components together to leverage more science. And then in between all of these are kind of the uncertainties, the physical parameters, the components that go into our modeling that we're really trying to learn about. So let's start out with the formation and evolution of these systems. So in cosmology, part of the standard growth of structure in the universe is the mergers of galaxies. So basically all galaxies in the universe experience numerous mergers, some of the major mergers over their lifetimes, and that's how they grow in mass. And we believe that almost all massive galaxies have black holes in the center. So these galaxy mergers can then bring those massive black holes together, and maybe exciting things will happen. Now, interestingly, even though these galaxy mergers kind of really smash into each other, and it seems like they're now completely mixed into a single object, it's actually very hard to get the two black holes to actually meet each other in the center. So kind of the physical process was first outlined 40 years ago now by Begelman, Blanford, and Rees, and you really rely on environmental interactions to bring the black holes together. So we start out at kind of kiloparsec scales where dynamical friction mediates the actual galaxy mergers and starting to dissipate orbital energy from the black holes. So this is when a massive object is moving in a background medium of things like stars, dark matter, gas. It creates an overdensity of material behind it, which then exerts a drag reverse acceleration force on it and starts to sink them down to the center. Now, once you get towards parsec or tens of parsec scales, the binary actually forms. It becomes gravitationally bound. And in that case, the energy of the binary becomes comparable or larger than the typical stars and stellar energy nearby. And in that case, you need to start thinking about the individual scattering of stars with the binary. And what happens is that, that you have this binary orbiting, a star will come zooming through, and it'll typically get ejected from the system, carrying more energy from the binary away that further hardens the system. Now, if you're able to get to even smaller separations, and if these happen to be systems with active gas accretion going on, then you can have a circumbinary accretion disk form around the system, and then torques from that binary can start to actually tug on the black hole pair itself and extract further information, extract further energy. So this is just an example of a 2D hydrodynamic simulation by Dan DeRazio showing kind of the interaction between these two. And this is a very active area of research. Now, finally, at the smallest separations, 5, 6, maybe 7 orders of magnitude in separation smaller than where we started, finally gravitational wave emission becomes important, further extracts energy, and eventually coalesces the system. And this is the phase that we're hoping to make gravitational wave detections, and maybe nanograv is already starting to see signs of this. Now, this is kind of the canonical picture that's been around for a while, and most of it seems to hold quite true, robustly, let's say, but there are still huge amounts of uncertainties through every single stage of this process. And excitingly, a lot of the work that's been done on this has actually been done here, in particular by Professor Holly Bockelman's group at different times. So for example, we don't even understand where these massive black holes come from in the first place. So we know they exist in most galaxies, but we don't know how their seeds form. And this is another very active area of research. In the dynamical friction stage, we don't always know how effective this is going to be, how sensitive we are to the initial orbital parameters, how quickly material is pulled off of these satellite galaxies as they pull in. And then the kind of classic element of uncertainty is in stellar scattering, where the loss cone of stars might actually be depleted. So you kick out kind of all of the stars that are able to scatter with the binary, and it's no longer able to harden. So Professor Holly Bockelman, especially in collaboration with Fazil Khan, has done a lot of work on this, and they've really shown in a lot of different ways that realistic galaxies that are not spherically symmetric, especially after merger, tend to replenish the loss cone, and hardening seems like it's relatively effective. So that seems pretty good. Very recently, a huge debate has come up in the community about whether circumbinary gas disks actually harden the binary at all, or whether they may actually soften them and try to pull them apart. This is a really exciting area of study, and I'll show a little bit of some of these simulations later if we have time. Okay, so my methodology in exploring this starts out from using the illustrious TNG cosmological hydrodynamic simulation. So I'm showing a movie of just a very small portion of one of the boxes of these simulations, showing how galaxies are growing, interacting, and merging over time. And what you're seeing here is mostly the distribution of stars as we move forward in redshift, which is shown up in the top left. So I start out by identifying the points in time where galaxies interact and merge here. I identify the black holes in those systems, and then I kind of extract all of the information about the local galactic environment. So in particular, the density profiles of gas, stars, dark matter, and what their velocity structures look like. Now, the reason why I need to do that is because these simulations, they're very large volumes of the universe, but that means that they can't resolve the detailed small scale physics. So once these black holes reach roughly kiloparsec scales or so, I have to switch over to kind of semi-analytic post-processing models where I kind of add in by hand the physics that we think is at play. So my approach is just to kind of use our state-of-the-art knowledge from a huge variety of studies to just try to incorporate everything that we understand on these small scales. And the unique aspect, I think, of this framework is that I'm really trying to use these detailed, self-consistently derived galactic environments at the same time. And a lot of what I'm going to end up talking about is kind of the even further stages down of taking these binary populations and adding gravitational wave signatures, seeing how detectable they are, and then doing the same thing for electromagnetic signatures being produced by the disks. So kind of one of the simplest ways to look at the results of this binary evolution analysis is this type of plot of hardening timescale on the y-axis versus binary separation on the x-axis. So binaries actually start out here on the right at large separations and then move down to the left. each of the different colored regions are these different environmental hardening mechanisms. And you'll see that actually each of them is very important for bringing the binary down to small separations. So the two black holes would end up just stuck at kiloparsec separations, not even a binary, just an association, unless these factors were at play. Also notice that up here on the y-axis, these are very long time scales. So this is about a gigayear here. So the typical lifetime of these binary systems is gigayears, and many of them do still stall, for example, at kiloparsec separations or at parsec separations, the final parsec problem. But many of these systems do eventually coalesce, and that's where we get our exciting phenomenon that we hope to see. Okay, so that was kind of a lightning version of the formation and evolution of these systems. And I should have said before, kind of throughout the talk, there are going to be kind of a few of these punctuations where it's a great place if people want to ask questions. So if anybody has a question, please feel free to raise your hand, and I can actually see that on my other screen here. Otherwise, I can keep going. Okay. And I cannot see the chat, so if anything comes up there, Steve, please feel free to jump in. Okay, so next let's talk a little bit about the gravitational wave signatures that these systems can produce once they get to small separations. So this is the plot I showed a second ago about these different hardening rates. Now we can make this a little bit more useful by focusing on the small separations. This is where they're producing gravitational waves. And instead of separation on the x-axis, let's actually look at frequency. So this is a kind of switching the order of the x-axis. So at low frequencies, that's larger separations, and then binaries tend to harden moving to the right. And you see, again, these hardening mechanisms are very important in producing that. But what I want to highlight from this is that these hardening mechanisms, the time that binaries take to evolve along these trajectories, actually maps directly to the gravitational wave spectrum that they end up producing. So if you were purely driven by gravitational waves, which is this green hardening curve here, which is a perfect power law, then you would produce this blue power law gravitational wave spectrum. And this is kind of the simplest estimate of a gravitational wave spectrum, a -2/3 power law. Now, if you include these environmental hardening mechanisms, that means that binaries harden faster than they would otherwise. So they have less time to emit gravitational waves, and that attenuates or decreases the amount of gravitational wave energy at low frequencies. So this is kind of a simplified version of the gravitational wave spectrum that we would expect. In actuality, the spectrum is composed of a kind of statistical distribution of binaries with different masses at different redshift distances away from us. And that causes a lot of Poisson variation in the structure of this. So kind of a more simulated, realistic version of the spectrum looks something like this, where one realization of the spectrum is shown here in the purple solid line. And then the individual sources that you can see above that background are the red points here. And then in the background are a bunch of other realizations. So in a number of studies, many of which were done in collaboration with Professor Taylor, we've learned that there's a ton of information that's encoded on this spectrum, not just the kind of the environmental interactions at low frequencies, but a lot of other information also. So in particular, the overall amplitude of the spectrum is mostly governed by the total mass distribution of black holes. The more massive they are, the stronger their gravitational waves. And we typically parameterize this with some sort of relationship between the black holes and their host galaxies. So for example, the M sigma relationship, which is a tight correlation between the masses of black holes and the velocity dispersion of the stellar bulges that they're embedded in. Now, at the high frequency portion of the spectrum, the number of individual sources and the amount of steepening over here in the high end really reflects both the eccentricity and the redshift distribution of sources. And then finally, as I said before, oh, sorry, the wrong direction. The kind of low frequency turnover, both the location and the steepness of the turnover, tells you about what types of environments these black holes are evolving in. So a huge amount of information is encoded in these distributions. But now So I know basically everybody here has heard about pulsar timing arrays before, but I think I would be remiss not to quickly mention the idea. And the idea is just that pulsar timing arrays use pulsars where LIGO uses lasers. So instead of using a laboratory experiment where we use kind of the synchronization of lasers across different arms, we use nature's timers, millisecond pulsars, which emit periodic, very regular bursts of radiation towards our line of sight. Now, to actually extract a gravitational wave signal, instead of interfering between two lines of sight, we actually look at the correlations across the sky from pulsars distributed across the galaxy. So this is actually a galaxy scale detector of gravitational waves. So that's the basics of pulsar timing arrays. What a lot of people don't appreciate is that just from the upper limits, as they've been growing over the last few years, we've already really been able to constrain fundamental science, fundamental aspects of the massive black hole population and also their host galaxies. So this is an example of some of the constraints from the NanoGrav 11-year data. This is based on techniques developed by Joe Simon, by Steve Taylor, by Laura Sampson. And here I'm showing a comparison of kind of your probability distribution function on the y-axis versus just a particular parameter in the M sigma relationship. So what that determines the masses of black holes. And to show that schematically over here, so this is the mass of black holes versus properties of the galaxy bulge, and this alpha parameter is just describing kind of the normalization of this relation, which is very actively debated study. So in this particular study, they can really show that there's some tension with this particular very popular model, the Cormandy and Ho 2013 model. So we're already able to make inferences here, and that's from the gravitational wave background. So there's also additional information that's encoded in these individual sources, and it's long been debated about, which aspect of this we should detect first, and when we'll detect the gravitational wave background versus when we might detect some of these individual sources that happen to be bright because they're either extra massive or extra nearby in the universe. So in a study a couple of years ago, we looked at, what if you make numerous realizations of the universe, how bright do these individual sources tend to be? So here I'm showing the characteristic strain of sources versus gravitational wave frequency on the x-axis, and the color is showing how frequently these occur. So the yellow stuff down here is essentially every realization of the universe these occur, and as you move up, these become more and more rare. So the current most stringent upper limits, or not quite the most current upper limits, recent upper limits are up here. So the kind of expected distribution of strains is only a factor of a few just below the current upper limits. And based on this study, we found that there does tend to be kind of this plateau in the amplitude of these strains at low frequencies. And once you take into account that we do expect there to be a gravitational wave background, one that looks kind of like this means that there's actually kind of a sweet spot for detecting individual sources. It's not just at lower and lower frequencies, which is true for the background, because there the individual sources get swamped out by the background. So it's actually over here at 1 over a few years where you're most likely to detect individual sources. And in our study, we find that we actually project optimistic prospects for these being detected. So from these simulations, we expect that you would see individual sources just within a few years of the gravitational wave background. And that's a little bit different from what many previous studies have found. So pulsar timing arrays are just one of the methods around. So there's also the space laser interferometer space antenna, LISA. So this is going to be a space laser interferometer that's kind of following in an Earth trailing orbit. And this has kind of millions of kilometer long arms that it can detect gravitational waves over. And to situate that in kind of the sensitivity parameter space, so pulsar timing arrays are up here at very low frequencies or periods of about a year. LIGO is up here at very high frequencies. And then in between is LISA right here. So mostly or largely, LISA will be detecting stellar mass systems, but they will also pick up massive black holes occasionally. So if we zoom in on the LISA portion of this parameter space, I worked with a student at Northwestern, Michael Katz, who really focused on how often can we detect these massive black hole signals in the LISA band. So one of the big developments that Michael did was he expanded our population of binaries from just looking at relatively massive systems, so in particular above 10 to the 6 solar masses. He extended that down robustly to all the way down to 10 to the 5 solar masses, which are a really important aspect of the population detectable with LISA. And the reason for that is just that because LISA is sensitive to higher frequencies, that means they can measure smaller mass systems as they're coalescing. And so those have to be incorporated into the analysis. So from this analysis, we find a LISA detection rate of something like 1 source per year. So 1 actual coalescence event per year. And note that that's really just these massive black hole systems. So only the sources of above 10 to the 5 solar masses. Okay, so that was another quick overview of gravitational wave signals. Are there any questions about that portion?
Look, I think I'll use my moderator prerogative and just ask about that last slide on the LISA
Sure.
prospects. So this is still based on Illustris, is that right?
Yes, that's right.
So are there any, what are the sort of new in development simulations that might be better tuned for Illustris predictions? For LISA predictions, sorry.
Yeah, that's a fantastic question. And actually that's a great time to advertise that Professor Laura Blecka at the University of Florida, we're working on a grant project together where we're actually going to be running a new generation of cosmological simulations that are focused just on the seeds of massive black holes. So this is going to allow us to simulate the universe at much higher redshifts and much lower black hole masses. And those are kind of the key sources that we're expecting for LISA. So I would say that that's one of the best possibilities of doing that. But there are, of course, numerous other groups. For example, the Romulus simulation group has also been working very carefully at looking on these lower mass black holes and their consequences for LISA. So there are great prospects coming up.
That's exciting. Yeah, thanks. Dusty, you have a question?
Hey, Luke. I was just wondering if you could comment on pulsar timing array's ability to probe the sort of final parsec problem by looking at the lowest frequency bends, and just kind of comment on the effects of like cosmic variance potentially affecting that.
Yeah, that's a great question. Let me see if I can quickly work back to a useful slide. So in my simulations in particular, the cosmic variance at very low frequencies is actually relatively small. And that has to do directly with what I was saying about the individual sources. So even though individual sources are kind of distributed at all frequencies, just because you have a much stronger buildup of the background at low frequencies, you have a much large population of systems there, and thus your Poisson variations just get much smaller in those cases. So I think this is somewhat model dependent, but I don't see a ton of variation at low frequencies.
Okay, great.
I do still think that's, sure. I do think that's something that's definitely worth looking into more, especially in the current context. Okay, try to get back forward. Too many slide transitions. Okay, so let's finally talk about the electromagnetic side of things. So there are a huge array of methods for trying to detect massive black hole binaries through their presence as active galactic nuclei, AGN. So that's when a massive black hole is actively accreting and producing emission. There's some really great reviews on this topic that I've kind of listed up here, but some of the main types of methods are kind of, so for example, looking at visual pairs of AGN. So for example, this is a Stephanie Camosa study in the X-ray where you can actually see 2 different point sources here. And this is also done in the optical. The most famous example is probably this radio source here at the bottom, where you can actually distinguish 2 very nice radio cores here that are very convincingly AGN. And to my knowledge, this is the the closest known pair of kind of confirmed black holes. They're at a projected separation of about 7 parsecs. This is usually called a binary system, but I don't think that it's been definitively shown that these are actually gravitationally bound instead of, maybe they're still outside of their spheres of influence, or maybe just the projected separation is small and not the actual separation. So maybe a binary, maybe not, still at parsec scale. So definitely well before the kind of gravitational wave emission regime. There are also a number of other mechanisms. So for example, there's X-shaped radiomorphologies that might be the sign of a jet that has flipped or been twisting. And what I will be talking about a good amount is periodic variability. So kind of this sinusoidal pattern in the photometry of AGN, or periodic outbursts up here in the top right, that might signal the presence of a binary. I'll also be talking about some subfield that Professor Renaud has really been revolutionizing, which is looking at the spectroscopic features about these systems. I won't have time to really go into it in too much detail, but just earlier this year, hard to believe that was earlier this year, there was a Nanograv white paper where we tried to really lay out the different exciting things that you can do with corresponding gravitational wave and electromagnetic emission. And there's really a wealth of physics that you can probe, probably mostly because you can just break a huge amount of degeneracies by both knowing the amount of gravitational waves from a system and the amount of emission produced by a system. So that's a huge lever arm for breaking degeneracies in your models. There are also some really cool kind of cosmological probes that you can use of making these systems into standard sirens, and there's a lot of cool results on that also. But please take a look at this if you're interested. So one very practical benefit from having these multi-messenger sources is you can actually boost the detectability of both the gravitational wave and the electromagnetic aspect. So for example, one of the best candidates is for a binary is 3C66b, where we might be seeing kind of orbital motion in the radio core of a system. So this is radio imaging of the location that the source is coming from. And models are suggesting that this could be actual motion of the jet attached to one of the black holes in the system. So recently, Nanograv, led by Caitlin Witt, used this source as a trigger for gravitational wave sources. And really excitingly, she found that just based on kind of constraining your prior parameter space, you can boost your sensitivity by up to a factor of 2 or so, which is really a huge factor, because a factor of 2 in sensitivity translates to a factor of 2 in distance, or a factor of 8 in volume. So that's a huge effect. And it's also really lucky that 3C66b happens to be at one of our most sensitive locations in the sky. So I think this is a really cool study and a really cool proof of concept for, I think, what's going to be happening a lot more over the next few years. Okay, but I want to spend a good chunk of time talking about periodic variability of Hdn, which is the topic that I've worked on a lot recently. So in particular, in the last few years, there have been these kind of growing samples of candidate binaries based on periodic variability in large surveys. So in particular, in the Catalina Real-Time Transient Survey, CRTS, they found about 111 binary candidates out of 240,000 AGN. This was led by Matthew Graham in 2015. Also, the Palomar Transient Factory, led by Maria Carisi, another Nanograv member, found a kind of consistent event rate or occurrence rate of these periodically variable systems. And Ting-Ting Liu, using the Pan-STARRS survey, which is a much smaller field of view, so they don't have as many possible systems to examine, but their upper limits are also consistent with this. So there's signs of a lot of periodic variability in AGN, and maybe it indicates the presence of a binary, but what would cause that? So what's the physical picture that we should have in mind? And the physical picture that's been developing is one of a circumbinary disk that I'm showing here in purple, and then 2 black holes, each surrounded by a circumsingle disk, and those are being fed by accretion streams that are crossing this cavity that's been cleared out. And we started to see a little bit of this in the animation before, but really some of the cutting edge work on this is being done by Diego Munoz. And this is showing one example simulation from a large number of suites that he's been working on. And one really cool thing about this particular set of simulations is it's actually using the same code base, a repo, for the hydrodynamics. And this is the same code that's used actually in the illustrious simulations. So just completely different scale of simulations here. So you can see that there's this outer region of circumbinary disk, a cavity that's being cleared out in the middle by the orbit of the binary, and then these streams of material that are coming in and feeding the individual black holes. So there are a lot of really, really exciting things that have come from these simulations, but some of the kind of most important to highlight is that the accretion here is actually dynamically driven instead of viscously driven. And this has some important consequences, including this accretion should continue all the way until the time of coalescence. And previously, this wasn't believed to be the case. So if the accretion was being viscously driven, once you get very near coalescence, that viscous driving becomes slower than the gravitational wave in spiral time, and the disk could actually decouple from the binary. But because it's dynamically driven, that doesn't seem to be the case, and you can have accretion all the way until merger. That also, the strong dynamical coupling there also leads to very strong periodic modulation of the accretion rate onto these black holes. So here's an example of the accretion rate onto the two components in red and blue here as a function of just orbital periods. So you see this very strong sawtooth pattern here, and the sawtooth is happening at roughly 5 orbital periods or so, and you can see the individual orbital periods also embedded within this. So this is for a kind of equal mass ratio system. If you look at non-equal mass systems, then they actually find that the accretion tends to strongly prefer going to the secondary, the smaller component of the two. So here I'm showing the ratio of accretion rates, or the ratio of Eddington factors versus mass ratio. And you can see that especially at a mass ratio of about 10 to 1, in a variety of different simulations, you're seeing 100 times more material going to the secondary than to the primary. So really interesting and not non-intuitive phenomenon seem to be coming out in these circumbinary disks. And what I set out to do was see if, based on the insights from these simulations, if we add that onto my set of kind of binary populations, what do we expect for periodic variability signatures? So I took my binary population and added models for periodic variability based either on kind of this hydrodynamic variability, where you're just changing the accretion rate onto the components. And as the accretion rate goes up, the disk becomes more massive and brighter, and that produces a sinusoidal variation. Or even if the disks are staying exactly the same, just their extremely rapid orbital motion can produce Doppler variations if you happen to be oriented along within the plane of the orbit. So that can also produce sinusoidal variations. So once I embedded this into a population, I could calculate kind of how often we expect to be able to detect these systems. So for Doppler modulations, we expect that in current surveys like CRTS, we can detect maybe one source or so. For the hydrodynamic variability, where you don't need to be oriented within the plane of the orbit, so a much broader range of viewing angles, you can get up to maybe 1 or 10 sources in current surveys. So that's a pretty small number here. But if you think about future surveys like the Vera Rubin Observatory, formerly LSST, then you can get up to dozens or maybe even hundreds of sources in that case. Now, the problem is that there are currently hundreds of candidates. So this seems to imply that there may be a large fraction of false positives, and maybe there's some sort of additional process that's happening in individual accretion disks that's producing additional periodicity above what we expect. So this is also a way of probing kind of the detailed fundamental physics of accretion based on these signatures. So that's kind of the hypothetical modeled population of what should be detectable, but what can we do with the actual population of candidates? So in a study in 2018 led by Alberto Cezanna, we considered the existing candidates, in particular from the Graham catalog, the CRTS catalog, and we wanted to see what their consequences were. So here's a gravitational wave strain versus frequency plot, and apologies for this particular upper limit that I've used here, but this is just kind of a reference of what a PTA sensitivity looks like, and kind of a reference for what the gravitational wave background at that sensitivity might look like. So if we plug in the binaries or the candidate binaries here, and if we marginalize over uncertainties in their mass and their mass ratio, we get strains that look something like this. So none of these sources are actually constrained by current sensitivities. Now, if we start to bin these sources together, then we're starting to get a little bit closer, but still not really constraining. Now, this gets interesting when you take into consideration that the candidates that we've identified are processed by, survey parameters, by electromagnetic selection biases, and so we would definitely only be seeing a small fraction of the total number of binaries in the universe. So if we use this population and extrapolate to what actually should be out there producing gravitational waves, we get a population that looks like this. And now this is starting to be a problem because individual sources are definitely starting to fall within the sensitive range of our detectors. And if you bin these together into a background, now it produces this kind of whopping signal that's fairly definitively ruled out by current measurements, though that might need a little bit of revisiting these days. So the implied background, if you assume that all of these sources are real, is basically ruled out. So again, this is kind of suggesting that there might be some sort of contamination, some false positives in the sample. And I should be clear that all of these initial studies, for example, Gravitational, were very careful to say that these are just candidates. They definitely weren't arguing in the first place that these were all necessarily binaries. There are a few ways of kind of decreasing this tension. For example, if you assume that there's significant bias in the mass estimates, but that still leads to kind of tension between the electromagnetic and the gravitational wave side. And I think it's worth emphasizing that just that tension itself is really exciting because the gravitational wave constraints, or maybe upcoming measurements, are actually being able to be faced against the electromagnetic observations. And at the Nanograv meeting, we just heard about another recent study about this population from Chengsheng Jin, working with Chiara Mingarelli and Jeff Hasmoon, where they took this a step further, and using the same population of CRTS binaries, they looked at, when could we actually detect or put constraints on these individual systems? And it's actually not too far in the future. So here is a hypothetical pulsar timing array sensitivity curve once the square kilometer radio array, SKA, is active. So by that time, a huge number of these systems will actually be able to be probed by these observations. In the Jin study, they also give kind of a ranking of the most probable candidates, and I think that's going to be really useful moving forward. Okay, so here I've been talking about kind of the tests of these periodic variability systems based on gravitational wave and electromagnetic aspects, the observables from these systems. But there's kind of also ways that we can dynamically test these systems. So I had the privilege of working with a student at Harvard, Magda Siwek, and what she was exploring is kind of the consequences of this strong preferential accretion onto the secondary component. So if you combine those strong preferential accretions with these very long giga-year merger timescales, that presents the possibility of significantly altering the mass distributions during in-spiral, which is something that nobody's looked at before. So what Magda did was she created a suite of different models for how this mass growth changes over time and explored kind of all of the different repercussions of this. So what I'm showing here is just doesn't matter what these particular models are, but based on the details of this accretion modeling, you can produce huge variations in what the resulting mass ratio in this case is. So for example, this is if these curves here, which have very sharply peaked mass ratios near unity, are from directly assuming that these results are kind of universally true. That also has important consequences for the resulting gravitational wave background and Hdn parameters that come out of this. So Magda calculated kind of the resulting gravitational wave backgrounds from these different models. And again, they produce a huge variation, kind of up to a factor of 2 or a factor of a few variation in the amplitude. So this is another really good way which both gravitational wave and electromagnetic observations can kind of constrain the fundamental physics, in this case, of accretion onto these binary systems. And because it does have consequences for both aspects of those, then leveraging the gravitational wave and the electromagnetic sides can again break degeneracies. For example, if you want to know that the increased gravitational wave background amplitude here is produced by accretion, as opposed to the intrinsic mass distribution of black holes, you need some external way of distinguishing those two. Okay, so that was kind of a long discussion of periodic variability, but one of the other kind of equally relied upon methods for identifying candidates is through spectroscopic or kinematic signatures. And what this relies on is this kind of distinguishing character or distinguishing feature of AGN and quasars, that they have these extremely broad emission lines. So for example, here you can see these extremely broad hydrogen lines. And those are produced just by the kind of trans-relativistic velocities of gas very near the central black hole. So we believe there's some sort of broadline region of emitting gas that's moving at 10 to the 3 to 10 to the 4 kilometers per second, which is up to 1% the speed of light or so. And that material, because it has such a variety of velocities and Doppler factors, its emission lines end up getting shifted left and right in the observed spectra. We also, through reverberation mapping, know that there's a very tight correlation between the radius of this broadline region and the continuum luminosity that's kind of reflecting or bouncing off of it. So this is a particular derivation of the scaling relation from Misty Benz in 2013, and there's actually a very small scatter of only 0.2 dex or so in this relationship, so a fairly tight correlation. Okay, so AGN produced these broad emission lines. And the reason why they're broad is because they're kind of tracing the dynamics of the environment. So one idea that people have had for a pretty long time is that maybe these dynamics can also be traced in the spectroscopy when these AGN are in binary systems. So there have been a number of studies over the years that have looked for either individual spectroscopic peaks, individual broad emission lines that are kind of offset from what you expect from the galaxy reference frame, or even looking for time variability of those offsets. And Professor Renaud and her advisor, Michael Heraklius, have really kind of pioneered and led this whole discovery space, kind of established this field. So this is just one example of kind of comparing the spectroscopic lines over a baseline of almost 10 years from a AGN, and based on the shift in the broadline character, the shift of the centroid, or even the lack of shift of the centroid, you can try to detect or constrain the presence of a binary. So the idea is just that these broadline regions will be moving along in the orbital motion, and then the spectral line will be shifted accordingly. So there have been some really cool kind of theoretical studies of this parameter space recently, especially led by Tamara Bogdanovich's group in Georgia, and also Professor Renaud's group here. And what they found is that there's a huge amount of information that can be encoded in these spectral lines. And that's because there's a circumbinary disk, there are 2 circumsingle disks, there are 2 black holes, and then each of these systems has a relative inclination to each other, varying irradiation patterns, maybe different velocity structures. So it's an extremely complex system, and it produces correspondingly complex emission lines. And those detailed emission lines can definitely provide a huge amount of information about the binary system. So I was kind of trying to break into this subfield and realized that quickly that this was kind of too complicated for me. So I wanted to start somewhere simple. And something that's always struck out to me is that this kind of characteristic relationship between the broadline region size and the luminosity of it should immediately tell you what types of binaries would be allowed in a given system. So let me expand on that a little bit. So we know that broadline regions, which I'm showing as kind of this part of the disk here with green wavy lines coming out of it, we know it has some kind of characteristic radius. And for that broadline region to trace the motion of the black hole, the broadline region needs to be attached to each one of the 2 black holes. So if the binary orbital separation is too small, then it actually interferes with this broadline region, or the broadline region can actually be outside of the orbit as a whole. So that means that the systems that we can detect these kinematic shifts, these broadline shifts, are only up here in the top, where the binary separation is above some critical separation that's related to this broadline region radiance. Now, we also need these velocity offsets or velocity shifts to be detectable. And as you bring the binary closer together, the orbital motion gets faster and faster, and that makes them more detectable. So there's actually some threshold, so there's some maximum separation that you can distinguish this orbital motion. So in addition to having kind of a minimum orbital separation, there's also a maximum orbital separation. And you can kind of just derive these based on the observed scaling relationships. So the tricky part here is that the minimum separation, typically about 0.2 parsecs, is very near kind of the characteristic maximum separation of about 0.5 parsecs, which means that it's kind of a very narrow parameter space that you could actually be sensitive to in these cases. The really tricky part about this is this term here. So what types of velocity offsets or velocity shifts you're actually sensitive to. Not only is that a very uncertain parameter, but there's also a strong power of 2 dependence here. So here I've used a fiducial value of something like 10 to the 3 kilometers per second. That's a detectable separation. And I've tried to, in this study, I tried to provide some kind of theoretical arguments for why this is kind of a reasonable expectation based on kind of the ideal situation. But when it comes down to it, I think the limiting factor is that broadline regions are just intrinsically highly variable. So here I've plotted the distribution of jitter, which is just the kind of variation from one observation to another of the centroids of broadline regions from a study by Duan in 2019. So you'll see that the distribution of jitter velocities comes up to many hundreds of kilometers per second. And these are just in typical individual AGN. Now, really, from first principles, you kind of expect that AGN in binaries are intrinsically very rare, something like 1 in 100, 1 in 1,000 AGN overall. So really, you want to set a threshold on this detectable velocity that you're quite certain won't occur at those types of event rates. So I think there kind of are strong reasons to think that your limiting sensitivity is actually relatively high, like 1,000 kilometers per second. So kind of the last thing that I want to talk about is a rabbit hole that I've gotten very excited about in really digging into these jitter velocities. So kind of the leading picture of how they're produced is a type of reverberation produced by the accretion disk around the black hole. So I've tried to kind of cook up my own simulations of these accretion disks in the last year or so, where you're modeling this accretion disk around the black hole shown here, and here we're varying the inclination angle. And then you trace the emission produced by that disk by kind of ray tracing in GR. So the resulting broadline emission profile is shown up here on the top, and I'm decomposing it into bins of Doppler factor, which are also shown down here. So the blue parts are very strongly blue shifted up to high frequencies, and the red parts are red shifted down to low frequencies. So kind of the canonical model of where this jitter comes from is that you have variations in your continuum source from near the black hole, and then that continuum emission reflects off of different parts of the disk and kind of captures its Doppler factor, so it captures its velocity shift. Now, the thing is that if your observer is down here, there's varying light travel times from different parts of the disk. So for example, this beam of light hits this blue shifted portion of the disk and then arrives to the observer earlier than a parcel of light hitting the back part of the red shifted disk that then later reaches the observer. So if you have a brightening of the central continuum source, first it'll be a blue shifted brightening and then a red shifted brightening later. So that can produce kind of this change in the typical velocity. So here I'm showing the difference in the emission lines as a function of time, where blue is the earlier differences, and then the green to yellow is the later differences. So you do see here that at the bluer part of the spectrum, you get this brightening corresponding to fading in the red portion of the spectrum, and then at later times that flips to a decrease in the blue emission and an increase in the red part of the emission. So, So if you model kind of the intrinsic variability that looks kind of like a tamped random walk from the central emission source, you can trace how that gets mapped out to the spectroscopic signatures in the disk, and you can find how much that velocity is varying. So this is still something that I'm actively working on, and that I'm trying to convince Professor Renaud to help me out or consult on with. But what I'm seeing so far is that for typical parameters of disks and for typical parameters of variations of continuum source, you only get these very, very small shifts in the resulting velocity. So here it's only about 0.5%, and in the resulting overall spectrum, it shifts of about 10 angstroms or so, which is a relatively small shift. So from kind of this preliminary analysis, which I'm still exploring, it seems like you need either intrinsic variability of your broad emission line region. So it's not just kind of a stable configuration, it's actually dynamically changing over time, or you need drastically more intrinsic variability from your illuminating source. Okay, so that was the electromagnetic side of things. And as we're getting just about out of time, I'll kind of skip a lot of the summary and just kind of take us back to our starting picture. So I tried to tell you about how these massive black hole binaries form through galaxy merger, through a variety of environmental interactions. They're able to reach very small separations and eventually produce gravitational waves. Those gravitational waves we're trying to detect with pulsar timing arrays, both in the form of gravitational wave background, also individual sources above that background. And what I didn't have a chance to mention was bursts of memory, which also are a very interesting topic. And then the multi-messenger aspect is the electromagnetic signatures of these systems. So in particular, periodic variability in Hdn or spectroscopic signatures of their broad emission lines. And in between these two, in between the electromagnetic and the gravitational wave, is really a wealth of physical uncertainty that we're trying to learn about and trying to probe. And I'm very optimistic that we're going to be able to do that in just the next few years, really. So with that, I think I'll close. Thanks so much.
Thank you very much, Luke. That was fantastic. Any questions from the audience? I know we've got quite a few people from Vanderbilt and Nanograv, so any questions for Luke would be welcome. And you're getting a virtual applause from Javi, and Javi also, okay, so I think Kelley was first, so go ahead, Kelley.
Hi, Luke. That was such a lovely talk. Thank you so much. I actually had a question about the simulations of the gas disk with the repo, just because it was so lovely, and I don't think I'd seen it. So can you tell me a little bit more? Sorry, about, was it 3D? Did they include feedback? You know, can you tell me just a little bit more about it? And don't worry, I'll read the paper. Sorry.
Sure. No, great question. I'm happy to talk more about this. Really excited about this. And again, this is something I wasn't directly involved with at all. So these are 2D kind of idealized simulations. So there's no feedback. There isn't even realistic cooling physics or anything like that. And the reason is that Diego Munoz, he finds that you need to resolve essentially thousands of orbits to get a really reliable steady state distribution to be able to study the details of the physics, for example, the torques and the accretion in these systems. So it's a hard problem. There are groups that are exploring 3D versions of this. For example, still using a repo, Magda Siwek, who I already mentioned, she's working on 3D versions of this, and in particular exploring kind of misalignments between the disks in the 3D regime. Then adding in feedback processes gets even more difficult, but I know the kind of GR-MHD community is working on that in the very kind of low orbit number regime. So I think we still have a long ways to go for a kind of fully comprehensive picture.
Thank you, Luke. I was actually thinking exactly about that misalignment problem and sort of the tilting of the orbital plane and stuff like that. But thank you so much.
Great. Javi next.
Yeah, I was wondering about your Catalina real-time survey constraints. In light of the common red noise process that nanograv has seen, has anybody thought to revise? Like, how do those results? How more consistent with an actual supermassive binary black hole population are those results? If you believe the nanograv, the nanograv range of 2 plus or minus a bit times 10 to the minus 15.
Yeah, that's a great question. So I didn't talk about this, but there might be a signal in the nanograv data that suggests we're about to detect the gravitational wave background, and it's actually louder than we expected. So in particular, it's louder than this upper limit that I've showed here. So I think for this particular case, I would say the same conclusion holds, although maybe a little bit less rigorously. So kind of from this analysis, we were guessing something like 90% of the sources would need to be false positive. So I think that could definitely be revised to, I don't know, maybe even guessing 50% or something like that. But I still think there's strong evidence that there's a large number of false positives. One of the ways of decreasing the tension between these observations is systematically lowering the inferred masses of these systems, but that actually could go in the opposite direction of trying to make sense of the possible nanograv signature. So again, this is kind of the quintessential place where we need to be thinking about both constraints at the same time.
Great, thank you very much, and really nice talk, thanks.
Thank you.
I was muted. Joe Glazer next, and then last question from Jesse.
Cool. So hi, Luke. Fantastic talk overall. It was really cool stuff. So at the end of the talk, you were talking about the variability and the ray tracing for the GRs, stuff like that. So I did my PhD at Drexel, where a lot of the people over there are working pretty heavily with the variability problem with AGN. So my question kind of comes down to kind of what the specifics that were included in the disk, like the specific models that you were putting in. It looks like it's a flat disk, but I'm not entirely certain if you did a dusty torus or something along those lines.
Yeah, great question. So far, I've just looked at a perfectly flat disk. I have allowed for arbitrary eccentricities and also not only kind of orbital motion, but also inflows and outflows. So it is still a highly simplified model, but I think that is kind of comparable to what people had in mind for this type of jitter. But it's definitely not physically comprehensive and should be expanded, absolutely.
Yeah, but still really cool, promising stuff on that.
Thanks. Okay, Jesse?
Yeah, great talk, Luke. Thank you. So I had one question, and then in the questions, I have now another question related to Javi's question, which I think is quite quick. You mentioned that the sort of tension with CRTS candidates is different if their masses are off. How much does it have to be, did you say?
I can't remember offhand, but I think we could kind of completely alleviate the tension with a factor of 5, if I'm remembering. No, sorry, half a deck. So like 3 or so. Interesting.
I'm just curious because it's to get the mass, I think you have to use scaling relations from single black hole like normal AGN, right? Which always has made me a little uncomfortable. And so I wonder if you can think of a reason why those would be systematically wrong in a binary after you've moved through the disk. I haven't given it that much thought, but that's a cool thing. And then obviously I think the last bit of your disk simulations is great. Have you thought yet about the timescales that you see these processes on? Are you just looking at like a light travel time?
So I haven't looked at that in too much detail. I've just made sure to that these kind of simulations are running for at least 10 disk crossing times or so. But that definitely does not incorporate kind of the viscous timescale changes in the structure of the disk or something like that. So it's definitely still very preliminary, not only in its physical structure, but its temporal structure.
Yeah. No, this is great. Thanks for sharing it.
Sure.
Okay, everyone. Thanks for the questions, and thanks, Luke, for the fantastic talk. So I'll see you all soon. Thanks again.
Thanks.
Thanks.
Bye-bye.